Alright, so in this video we're going to solve another problem which consists of a differential equation, and this one is also perturbed by a small quantity. Instead of being perturbed in the form of the differential equation itself, we will see that this one is going to be perturbed through the boundary conditions. Alright, and so the setup of this problem is the following one. Let's imagine we have an experiment where a long and thin rod is just touching a cold reservoir over here, which is insulated at the top, in order to provide a boundary condition at the bottom that is t is equal to t0. All right, and the bottom should probably be when x, the curvilinear coordinate, is equal to L, where capital L is the total length of this rod. All right, and then this rod actually is going all the way to the top of the room, and to the top of the room we have the roof, and we are interested in the temperature exactly at the roof. All right, so what we would like to measure in this experiment is the temperature at the roof. All right, so I'm just here pretending that we want to do something out of this problem and this experiment, right? It might not be fully realistic, but that's the, just imagine this is a problem we want to face. And unfortunately, we have a sensor that is able to measure the temperature along the rod anywhere, but unfortunately, we can't put this sensor as close as we want to the roof. And so the closest point where we can measure to the roof is at a small distance, epsilon times L, to the roof. All right, so we could measure the temperature all along the rod, but we couldn't get closer. All right, and so, well, this is just the setting corresponding to this problem, and what we just willing to do in this case is to solve the differential equation that consists in modeling that problem. All right, and so the governing equation that we need to write is a heat equation, which is in 1D, and we're going to look at that equation just in a stationary format. All right, so if you come back to Fourier's theory of heat transfer, you remember that there should be the second derivative of the temperature multiplied by the thermal conductivity is equal to the heat generated per unit volume. All right, there's a slight difference here, is that the thermal conductivity is not constant in space. So we're going to assume for some reason that the thermal conductivity here is not constant. All right, why not constant? Well, in fact, just because I designed this exercise to have something different from a linear equation and just to change a little bit. All right, so what do we observe in this problem is that the equation we want to solve is not first equipped with boundary conditions. So let's write the two boundary conditions. We have that a temperature at a distance epsilon L, let's say from the roof, is equal to T1, a certain temperature, and the temperature at the bottom of the rod in the reservoir is equal to T0, which is smaller than T1. All right, and then second thing, the problem that has been written here is not written in the dimensionless version. All right, although we have clearly identified the small parameter, epsilon here, which is a parameter that is much smaller than 1. So before proceeding with a perturbation analysis of this problem, we should rewrite the problem in a dimensionless version. All right, so to do this, what do we need? Oh, probably before proceeding further, we could also specify k. Just as an example, as I said, I want something nonlinear, and it might be strange, but why not using something like 1 plus x over L squared. All right, this is just to make something simple. All right, so the thermal conductivity, you see, is something that is, and we should give it the right units. It's going from K0 when x is equal to 0 here at the top, and the thermal conductivity increases as we go down this rod, and when x is equal to L, this is equal to 1, so you see that we have doubled, in fact, the thermal conductivity. This is something that could be, for instance, played with the cross-section or the material or whatsoever. All right, so we need to put it in a dimensionless version. So put the problem in a dimensionless version. All right, we need a characteristic distance, x star, all right, because this is the independent variable of the problem. So we can think just a minute of what we would use. Think of it, but x is a curvilinear abscissa that is running along the edge. We have two distances in that direction. We have epsilon L and we have capital L. Remember, we should not use the small quantities to define the reference scales, at least not to start with. This is something that we might do very soon, especially when there are boundary layers, but not to start. All right, so definitely there's no other option than to use the total length of the rod, so capital L. We need to find a characteristic temperature. In this problem, we have two different temperatures. We have T0 and T1, which are the two temperatures at the bottom and at the top. In this case, I'm going to do something slightly different. I'm going to, because I don't want to choose between T0 and T1, so I'm going to use something that is a linear transformation or combination of these two quantities. And then I could, for instance, rewrite that the temperature T as a function of x. I don't want to use a characteristic temperature right on, but I can say that the temperature as a function of x is T0 plus T1 minus T0. So the difference in the two temperatures multiplied by a dimensionless version of the temperature, which is going to be expressed as a function of xi, and xi is xi of x. All right, and xi is just defined by using the characteristic length x star. All right, and so why do I do this? I think we understand that this choice for the temperature is instead of just scaling by a certain quantity here, which would be the reference temperature, I scale and then shift. And the aim of that choice is to transform the boundary conditions into something simple, right? Because let's see what this would give when capital T is either equal to T0 or equal to T1. All right, so if T is equal to T0, it means that T0 is equal to T0 plus T1 minus T0 times T tilde. That means T tilde is equal to 0. And when T is equal to T1, it means that T1 is equal to T0 plus T1 minus T0 times T tilde, meaning that the dimensionless temperature is equal to 1. All right, so you see this choice was clearly made on purpose in order to have the temperature running from 0 to 1. Okay, that's a trick to keep in mind, and I, of course, would fully encourage you to follow this procedure, especially when you solve boundary value problems, where the unknown parameter runs from something that is identified as small, which will be transformed into 0, to something that is much larger, or that is larger, T1, which will be translated by 1 after rescaling. All right, so we just actually here follow the standard procedure to write a dimensionless version of a problem. And then once this is done, we need to bring this back to the original equation. So let's see what this gives. We have a first derivative with respect to x. Let me first probably just rewrite the governing equation to start with. So governing equation is first derivative with respect to x of this product. All right, so I'm going to just here to use a chain rule in order to expand this in something like this, plus the first derivative of k times the first derivative of t, and this is equal to q. All right, so if we want to rewrite this, so I need to substitute for k its expression, but we still haven't computed first derivative of k. So this will be k0 multiplied by 1 plus xc squared. And this is going to be, so the first derivative with respect to x0 is k0 times 2 times xc, and divided by L, all right, because this is a derivative with respect to x. In some sense, we could have just written this is a first derivative with respect to x. So we want to differentiate k with respect to xc, and then divide by dx over dxc. All right, and since x is equal to xc times L, this here is 1 over L. All right, so that's just basic principles. You shouldn't be afraid with that, and you should either make any mistakes, so don't forget this. There's a very good way to remember you need this 1 over L here, is that you see there's one derivative, so you should keep the units of x in the denominator over there. All right, so once this is done, so let's just substitute this into the equation, and probably we can divide left and right by k0 right away. So on the left we have 1 plus xc squared multiplied by the second derivative of t with respect to x. So you see that the second derivative of t here, it has a constant that will vanish in both this term and this term. So the only thing that will remain is this one. So we'll have t1 minus t0. We have the second derivative of t tilde with respect to xc. And this is a second derivative with respect to x. So we have divided by L squared over here. And then plus 2 times xc times t1 minus t0. K0 will disappear on the right hand side. And we have an L here coming from the first derivative of k. And we have another one coming from the derivative of t with respect to x. All right, so we see that we can then multiply left and right by this quantity here. All right, and so this will give 1 plus xc squared times the second derivative of t plus 2xc first derivative of t is equal to ql squared over t1 minus t0 and k. And we can call this quantity q. All right, so the problem we want to solve is nothing but that equation here. Is equal to q, and it comes with two boundary conditions, which are t of epsilon, t tilde of epsilon is equal to t1, that is 1, and t tilde of 1 is equal to 0. right? And so the problem here, in fact, as I said the problem before, would be what's the value of T tilde of 0, right? So we see that the temperature is something, the dimensionless temperature here as a function of xi is something that is running from epsilon to 1. It is equal to 0 over here. We just said that in our dimensionless version, it is equal to 1 over there. And this is T tilde of 0, which is 1 plus something small. And we would like to determine what's the additional small quantity over there. In other words, you took a measurement at a given point, all right? So you measured the temperature here, and you would like to know, based on the distance from the support, you would like to know how to compensate for this discrepancy, so the fact that you did not measure exactly at the roof. All right? So we'll see a little bit later that this equation actually has a closed form solution, right? So you could use a closed form solution for this problem. But in more complicated cases, you might not necessarily be able to solve that equation in closed form. And so by solving the equation in closed form, so exactly, you would know exactly how to compensate. All right, instead we're going to take advantage of perturbation methods, procedures, in order to solve the problem in a different manner. All right, and so we do observe that we have a differential equation problem here. The differential equation is not perturbed by the small quantity. The place where the small quantity appears is where the boundary condition is applied, all right? So this is the second case of the cases that I have introduced earlier in video E1, all right? So if you haven't watched this video yet, it's time to go back to that video and check it. And I was just saying over there that the small quantities could appear at the places where the boundary conditions are applied, all right? And so if you face such a case, keep in mind that the solution to this kind of problem is to just translate the boundary condition, translate the problem, or transform the problem. Let me just write translate the problem with boundary condition at a perturbed position into another, and of course, hopefully simpler problem with a slightly different value of the function at a hopefully simpler point or position. In this case, the general format of the general solution of that equation can assume a simpler form when we want to express the boundary condition at 0, because many terms disappear, and that makes it much easier. And so in this case, what I'm just saying here is that instead of solving the original problem here, we're going to solve another problem which has the same differential equation, all right? I just copied to make sure we are fine, is equal to Q, but the boundary condition is changed into boundary condition at a simpler place or location. Okay, this is what I mean at a simple point or simple position or location in space. And this one plus question mark is something that is a quantity that might be much easier to deal with, because this is only the value of the function, and this is not where the function is evaluated. All right, we will see that this question is probably, well, this way of tackling the problem is probably not strictly necessary for 1D differential equations, but as soon as we solve differential equations in higher spaces, then it might be really interesting. All right, and so to do that, what we need to do is to expand the boundary condition. All right, if you keep in mind that you expand the boundary condition in its neighborhood, then you know exactly how to transform the boundary condition. And so to transform or to expand the boundary condition, we're just going to write that the temperature at epsilon is in fact nothing but the temperature at 0 plus epsilon times the temperature at 0 plus epsilon square over 2, second derivative here, and so on and so on. Okay, that's just a series expansion of the boundary condition at epsilon, which is at 0, which allows us to express the boundary condition at epsilon. All right, and so this boundary condition here is going to be replaced by that boundary condition here. All right, and so once we have done this, then only we can use an ansatz. Okay, so first you expand the boundary condition, and then as usual, you use a regular ansatz. Why regular? Because you see that the problem is not really singular. We haven't changed in the unperturbed problem, we haven't changed the nature of the problem. In the unperturbed version of the problem, we would just have measured this quantity over here, and t tilde 0 over here, and t tilde 0 would just be equal to 1, all right? So clearly this is a regular perturbation, so we can use a regular ansatz. Okay, so in this case, just going to write t tilde is equal to t0 plus epsilon t1. And I will deliberately stop early enough, because the purpose here is just to illustrate the method and not to go all the way down too deep into the equations. So we need to substitute this into the governing equation. The governing equation is, you see, is linear in t tilde. So that's quite easy. We have 1 plus xi square t0 plus epsilon t1 and so on, plus twice xi epsilon t1 and so forth is equal to q. All right, so that's the governing equation. Don't forget that we need also to substitute this into the boundary conditions. All right, so let's start with the boundary condition at epsilon over here. Okay, but of course now this will disappear, and the only thing we keep is the right part. All right, and so this gives us t0 tilde plus epsilon t1 plus higher order terms plus epsilon t0 prime plus higher order terms. This is equal to 1. And we have another equation, second boundary condition, which is t0 tilde of 1, epsilon tilde t1 of 1. This is equal to 0. All right, and so this gives two problems, especially if we just stop after the first correction. So at leading order, we have the same equation as the unperturbed, all right? So I'm just going to copy it one more time. Oh, I forgot the derivatives here, I'm sorry. So we have the second derivative of t0 twice xi. First derivative of t0 is equal to q with the boundary conditions which are those of the unperturbed, all right? So t0 at 0 is equal to 1, and t0 at 1 is equal to 0. And so you see that this problem here is exactly the same problem as the original problem, but in this case you would just have assumed that the temperature you measure is exactly located at the roof, all right? So you would kind of neglect this and assume the temperature is precisely measured at the roof, although it is in fact measured at a certain distance from the roof. All right, so this is the unperturbed, okay? So the interpretation is very easy and not different from what we used to. And then the first correction, you see that because of linearity over there, we have exactly the same equation governing T1, especially on the left-hand side, because on the right-hand side we have 0. All right, in some sense you can imagine that this is q plus 0 times epsilon, and we keep all the terms which are the similar powers of epsilon left and right. Then the boundary conditions, we have 2. And we see this is quite interesting, and this is where we have exactly the signature of what we did earlier, okay, which is something you will recognize in these type of problems. All right, so the second boundary condition is easy, all right, so I won't discuss this too much, all right, but the most important one here, I need to highlight something here, is this equation, where in fact you see that instead of having T1 tilde equal to 0, which is in fact what you would have obtained from the original problem by just substituting the ansatz in the boundary condition. So if we would have here T tilde of 0, and if you substitute the ansatz over here, you see this is what you would have obtained. You would have obtained this. All right, but instead, thanks to the expansion we made for the boundary condition here, you see that the first derivative of the leading here, of the leading solution, comes into the picture. And why? Because of this expansion, all right? So we can backtrace the occurrence of this term, and we see that this is clearly this guy here, which comes into this term here, which is responsible for this first correction to the boundary condition. All right, so how does it work next? Next? At leading order, you can determine T0 tilde as a function of xi with the two boundary conditions. Although this is simpler than the original problem, probably a little bit, but not too much, because the format of the equation is the same. You see, the format of the equation is the same as the format of the original problem. All right, same as what we have here. The only difference is that we impose the boundary conditions at simpler points, all right? So we do expect here something slightly simpler than original problem. But it's okay. And then I don't write the full solution here. We will see that in a minute. And then we can go to next order. order epsilon, and we can get T1 tilde as a function of xi. We solve exactly the same equation again, which is now much simpler because we don't have any right-hand side. However, we have another boundary condition here, all right, which is not much more complicated than what we had before. All right, so that's also something we can compute. And so finally, we'll be able to compute T tilde, come back to the ansatz as T0 tilde plus epsilon T1. And if we are interested in T0 of 0, we'll have T0 tilde plus epsilon T1 of 0 plus higher order terms. So because we see from the boundary conditions that we have used here and there, we see that T0 of 0 is equal to 1 and T1 tilde is equal in fact to minus first derivative of T0. All right, so if we are just interested in the correction, all right, so the value 1 that we have here is the value measured where the probe is, and the value of the temperature at the roof is what we said is something that is slightly larger. So we would hope that this derivative is negative, all right? So we increase, and we slightly increase the value that is measured at epsilon over 1 in order to get the temperature at the roof. All right, and so at the end of the day, if you just want a procedure that aims at correcting a certain measure, you see that you don't necessarily have to solve the equation all the way down to the second order, but the correction that you need to the measurement is something that is only expressed as a function of the leading, and in this case, the first derivative of the leading order solution. All right, so just to give you an example here of how this looks like, I've put the equations in Mathematica, so we're going to go through these equations. I just define here the governing equation with the boundary conditions, T of 1, 0, and T of epsilon is equal to 1. I just defined here K as a function defined as 1 plus x squared. Keep in mind here that x is the same symbol as xi used before, and I also used value equal to 1 on the right-hand side over here, which, by the way, could be incorporated in the scaling you used or we used for t. The exact solution to that equation is a bit involved, but it's not impossible to manage just by hand calculations. All right, I just extract the solution from this root from the solver, and then I plot it. All right, and this corresponds to what we have earlier. So we have a value of the temperature as a function of xi, or as a function of x in this problem. And the boundary condition that we have used is that temperature is equal to 1, where x or xi is equal to epsilon, okay? And in this case, I have chosen epsilon is equal to 0.5. All right, and so this is exactly where the problem was, the boundary condition in the problem was imposed. And then what we were interested in is this value. But of course, the solution of the problem is valid way beyond epsilon, right? Because we could just extrapolate or use the solution, the exact solution to extrapolate. It's not an extrapolation in the sense of what you could do with a spline interpolation or whatsoever. All right, so we can just use the exact solution of the problem outside this range because this is just a heat equation. And as a function of epsilon, here we got here the temperature at the roof. So this is T tilde at the roof. All right, this is how it's defined. Temperature at the roof. This is the exact solution in which x is replaced by 0. And this plot just shows the plot of the temperature at the roof as a function of epsilon. And so you see that as a function of epsilon, for instance, 0.05, this tells you by how much you need to correct your experimental data. All right. And so, of course, what we would like to know is this calibration, some sort of calibration scheme or sheet or calibration equation. And that's what we would like to establish. All right. And so in order to do that, what we can do is to solve the problem with the perturbation method. So instead of solving the original problem, you see here, we solve another problem where the boundary condition is now T1 is equal to 0, and especially T0 is equal to 1, and not anymore T epsilon is equal to 1. All right, so we have changed the boundary condition from this to what we have here below. You see that the expression we end up with has in fact the same format, but is much simpler. Why is it much simpler? Because by replacing epsilon here by 0, many terms have disappeared. All right, this is the same format, but for instance, this one, when epsilon is equal to 0, we got the log of 1, which vanishes. All right, this one disappears. And we have many things that do disappear. And at the end of the day, you see that the solution you have is much simpler. Then, after having computed T0, which is a leading order solution, remember, we had to compute the first derivative of T0, and the change in the boundary condition at the next order is the value of T0, the first derivative of T0, when x is equal to 0. And this is this quantity here. All right, that's the quantity that matters. And as I said earlier, hopefully this is something that is negative. And indeed, we see that this is negative. And this corresponds to, so negative that quantity corresponds to, in fact, to the slope in that calibration scheme or correction factor. All right, so if we want to further illustrate the solution of the problem, we could plot here, we could plot T0. So this is the exact solution again in solid blue. That's the solution we got earlier. That's what the leading order solution provides. So the dashed orange line over here, which is the one corresponding to assuming that the measurement we took over here, we just put it over there. And so in fact, you see that the distribution of temperatures along the rod is slightly different. But if we go to the next order and if we want to solve it, although this is something that is not strictly necessary for compensation operation, but though we can do it, you solve for T1. This is another expression you get, which is not much more complicated than what you had at the leading. And if you add now T0 plus epsilon T1, you see that the solution comes very, very neatly close to the exact solution of the problem. And if you want to understand now this calibration thing or this calibration procedure, that's something we can do quite easily. And just using 1 minus BC1 times epsilon, you see that we get here in dashed orange the prediction for the correction that is obtained with the perturbation method. And you see that it does a pretty decent or good job until values of epsilon, let's say probably 0.04, and then it depends, of course, on the accuracy you want, and the accuracy you want to reach compared to the accuracy of the measurement. All right. Okay, so I just wanted to, with this very simple example here, I just wanted to introduce you what to do when there is a perturbation in the place where the boundary condition is applied. All right, and in this case, we see that there was a perturbation where the boundary condition is applied. The trick is very simple. You need to expand the boundary condition in the neighborhood of something that is easier, which is 0 in this case, and express the value in that neighborhood, which is the boundary condition of the original problem, in terms of the boundary conditions where the point is simpler. And of course, by doing so, you understand that you have to use a series expansion. So derivatives of that function will appear, they will pop into the problem. And in fact, these values, because they will come at higher orders, these are the quantities that will be used in order to change the values of the boundary conditions at higher order. And so this will dictate somehow how the corrections will appear at higher orders. Hope it was clear. And there are many extensions of this approach into 2D or 3D, which are a little bit more complicated. Probably I will post a few more videos on those, all right? But this video here is clearly the one that is mandatory in order to understand what to do when you face such problems. All right, so keep going and enjoy.